Swayam Prabha. Digital India. Educated India.
Okay, yeah. So, yeah, in some cases you would have definitely seen that the performance of plug flow is exactly identical with the performance of batch. Okay. Physically, can you see any correlation between these two? This is a flow reactor where continuously you feed, continuously you are getting. The other one is batch reactor, but still you will get the same given the same volume, you may get the same time for some conversion. Here also I can calculate tau, no? In this also we can calculate what is the residence time required for certain conversion, and residence time is equivalent to volume, correct, no? Volume, residence time is equivalent to volume, right? And of course we are talking about only reaction time. When you talk about batch, when you are comparing plug flow and batch, you are talking about only reaction time, right? The other times you cannot take. So definitely then plug flow is better in that case, because it is continuous. You do not have to discharge, you do not have to again refill, you do not have to again all that, once you start, years and years you can run the plug flow reactor all the time. Okay, good, yeah. But physically, can you say that why both are giving same under certain conditions? And to give you the clue, that condition also I will tell you. The condition is constant density system. Okay, so under constant density system, why the performance is same? Can you imagine something? Because you have to also extend your imagination. Okay, why? Because you already know that information, that plug flow is also equivalent to batch under some conditions. But normally you should have a question, oh, that is a batch reactor, this is a continuous flow reactor, why same? And mathematically if you calculate, you will get the same timings or same conversion for a given time. You get that. But did you think a little bit of extension other than thinking that okay, this question will come in the examination, so let me do somehow. Okay, simply the here length by velocity coordinate is replaced by length by velocity will give you what? Time. That time, if it is just replaced in a batch reactor time, both are exactly same. That means the time here with respect to space is equivalent to the time of reaction. So that means if 10 seconds, let us say you are here and you can have some conversion, you can find out what is the conversion at this point, and same 10 seconds if you wait in the batch reactor, if the constant density system is there, you will also get the same conversion. How do you define plug flow?
Same residence time. Every molecule spends
same residence time.
Here also same.
Okay. In batch reactor, what will happen?
Same.
That is the one simple concept. In batch reactor, you are not allowing those fellows, and then you are waiting for either 10 seconds or 20 seconds or 100 seconds. You are arresting them. They have to be there. Okay. Whereas here, by definition, for reaction to occur, certain reaction, that means 90% conversion or maybe 80% conversion to occur, you also need certain time here, right? And by the definition of plug flow, all the molecules have to spend exactly same time in the plug flow. Whereas in batch reactor, there is no way for the molecules to escape. So that is why all of them have to spend exactly again 10 seconds to get this 90% conversion. That is the timings. That is the reason why this can be simply replaced by a batch reactor if you have a constant density system. What do you mean by variable density system? Particularly for gas phases, and all liquid phases can be taken as constant density system. That is why in the examination, I am also giving some clues in the examination. If I say that a liquid phase reaction taking place in a plug flow reactor, that means you are talking about constant density system. Okay, good. So in the variable density system, particularly for gas phases, gas phase reactions, when there is difference in moles, that means either 1 mole giving 4 moles, or this may be reverse also. This is also density, change in density, but here you will have less volume at the end, because 4 molecules giving you 1 molecule here, whereas here 1 molecule giving 4 molecules, okay, 4 moles. And then you also know that at constant at NTP, STP, yeah, 22.4 latest it will occupy, all that things we know. So then we can easily calculate under given temperature and pressure conditions what will be the increase in volume. Okay, what will happen now inside plug flow reactor when I have this kind of situation? What will happen? No, please remember that in a flow reactor pressure is always taken as constant. Volume increases, pressure increases if you put them and shut them.
Volume increases, so time decreases.
Decrease of residence time.
Since the kinetics varies.
Yeah, the time of flow now changes. Why? Because here let us say that also 4 molecules, 1 mole giving 4 moles, suddenly all that volume is not increasing. That volume also depends on how much conversion. Depending conversion, if I have some 10% conversion here, volume expands so much. You can calculate that. Okay, and then if you go slightly inside, then maybe it has come to half, then the conversion is, let us say, half, for example 50% conversion. You can also find out what is the volume. That volume, because pressure is constant throughout, that has to reflect only in acceleration, right? That has to, because there is a way now for these molecules to escape, because there is a continuous flow. On the other hand, in a batch reactor, same reaction I conduct, right? So 1 mole will give me again 4 moles there, no escape, so everything is shut and constant volume, because I am taking rigid batch reactor, rigid, okay, that means walls are very, very strong. So then what will happen now? Pressure increases. In fact, that is the technique used by Levensspiel to measure for gas phase reactions kinetics. You can now find out, depending on conversion, what is the increase in pressure, not volume, batch reactor total pressure. Now from total pressure, if you know the components, you can find out partial pressure. So using partial pressures and time, you can also find out the kinetics, whether the reaction is first order or 0 order or no order at all, and the format of the rate equation you can get from that data. That is why beautifully it is used, and that is also possible, it is a crazy idea, possible to have the variable volume batch reactor. How do I do that? I will take balloon where the elasticity is very, very high, easily it can expand. That is elasticity very high means easily expands, no, right, expansion. So when I put this 1 mole and then I have the conditions for the reaction, then at the end of the reaction, if I wait for 100% almost, right, then what will be the volume of the balloon now? 4 times, freely expanding, I mean without any resistance. So even that information also can be used for finding out kinetics, and this is what you have already done if you would have used the Levensspiel book. I think it is in 3rd chapter, that kinetics chapter, where at the end he has given the variable volume and also given very nice problems. How do you find out kinetics, how do you find out K values using variable volume batch reactor and also constant volume batch reactor. But here for our discussion, what we have to see here is, when I have the gas phase reaction in plug flow, the gas expands and then it moves faster. Okay? So when it is moving faster, then the residence time of those molecules, I mean, yeah, it will be less. So for a given volume, conversion will be less. For a given volume means for a given t value. Okay? Yeah. So that also you should have calculated. That means variable volume, what is the conversion, and for a given time, for example, or constant volume, what is the conversion. Because variable volume, particularly when you have 1 mole giving 4 moles, what will happen? Gas expands. What will happen to concentration? Decreases. When concentration decreases, rate of reaction will be less. So when the rate of reaction is less, then more time. You see, you don't need any expressions at all. You don't have to write a equation for each and everything. First, I think that like a story you have to discuss. Then if you want to exactly find out, okay, now what is exact conversion or what is exact time for a given conversion, then that means numbers when you come, when you ask, then you have to use mathematics. Otherwise, to explain subject I don't need mathematics. But please remember, in engineering mathematics play a great role, because every engineer has to quantify. Anything you have to quantify, right? At the end, when you are saying that okay, my reactor volume is 1 meter cubed, and people will ask you, you cannot simply say that like gods only can say that, okay, use 1 meter cubed, you can't question them because they are gods. But if I give that, you will 100 questions will come, sir, why 1 meter cubed, sir? Like you already told, no, I told 7 meter cubed, you say 0.7 meter cubed. You question me. That means to prove that I need mathematics, and then I have to say whether you are right or I am right. For that, mathematics will come into picture. That is why mathematics and engineering inseparable. Medicine to some extent they can escape. Okay. Otherwise, there are also tremendous amount of mathematics in medicine also. When they go to research level, to give aspirin tablet, we don't need any mathematics, because we also know when to take aspirin tablet. Okay, all of us, even without being doctors. Okay, so that is why the mathematics part comes only when you want to quantify. Please remember that as engineers, and quantification is a must for any engineer. You have to tell at the end, okay, so much is the diameter of the pipe, use this. I am not talking about reactor, anything. Okay, I think heat exchanger area is this, 10 meter square. How do you get 10 meter square? You have to calculate. How do you calculate? You have the heat transfer equations, right? Design equations. Same thing, even I think distillation column, anywhere you go, mathematics automatically come, because you have to finally tell that this is the diameter, this is the height, this is the composition, all that. Good, okay, good. So now I think you know the difference between the batch reactor and when you will have different conversions for a given volume, or when you have the same conversions. Okay. So that is one information which I want to tell you. Okay. So the other information, just the design expression for this now, right? The design expression. For design expression now, yeah, how do you write the design expression depends on what kind of system you have. Have you heard of what is called distributed parameter system and lumped parameter system? Okay. This comes as distributed or lumped. What is distributing there?
Lumped.
Yeah, I want you to, I want perfect understanding for you. So that is why I am asking, what is distributing there?
From the
Concentration, and if it is non-isothermal, temperature is distributing from this end to that end. Whereas in a mixed flow reactor, when you want to write the balance, so there, yeah, only inlet you know what is entering, and only outlet you know what is entering. So, but in between, if you want to write the balance, you cannot write, because there is no change. You cannot see any change. There is change between inlet and outlet also will have exactly the same conversions as inside, right? In fact, that is the approach taken by entire BSL. You know who is BSL? You don't know BSL? That you should know. Only you are telling very feeble voice about Stuart. Okay, but I think with louder voice, okay. All of you have used about Stuart Lightfoot? What is the name of the book? Transport Phenomena. Where are these people from?
University of Wisconsin.
Which country? US. Okay, good. Yeah, and when they were very young, they wrote that book. Right? I think all of them are around 30-35. And they changed the thinking of all engineers. It is not only chemical engineers, even other engineers thinking also they have changed. Till then, everything, I don't say everything, but many of the things are only empirical. Doing experimental work, finding out correlation. That is why you have a lot of correlations when you are designing heat exchangers, mass exchangers like absorption columns, distillation columns and all that. These people came and told that even in engineering we can write mathematical equations and then we can solve them and then we can get the constant everywhere. You see, Bird, Stewart, Lightfoot, there is only one uniform exercises what you do. At the end what you get all the time is either it is velocity profile, concentration profile, temperature profile, that is all. The moment you know concentration profile, velocity profile and temperature profile, using that with the distance, profile means with the distance only, using that you can find out what is called flux. How do you do that?
Take the molar.
Yeah, we have Fick's law, Fourier's law, Newton's law, that is all. If you now go back and see, the entire book is only that, but the complications depend on what kind of balance you write, what kind of system you take. But at the end all the time again writing a differential equation and then solving that and solving as a conversion or some parameter as a function of distance. Of course, unsteady state also you can take, then you will get partial differential equations. Partial differential, that means now that parameter concentration changing with time as well as place. That is all, the entire transport phenomena is that, but the philosophy is that. But the moment you want quantification, you have to take one particular problem, write the material balance. Where do you write the material balance and energy balance? When there is a change, you take a small element, that is what we are going to take now. This is the small, I am showing a big element here, but that is supposed to be very small element. Okay. So, then we have to write what is entering, what is leaving, what is reaction in that. Okay. So, we call this one as volume, fine. This volume is dV, this is Fa, it is not Fa naught, somewhere inside I am taking. So, this will be Fa plus dFA, that is very simple. Okay. dFA, and then now we will we have to write the overall balance, right, and the overall universal balance what we have, we are only writing for isothermal. So, we are only writing for mass, and when you talk mass you have to always talk about one particular component. Please remember that I am repeating many times. Okay. Whereas for heat transfer everything is together, okay, the entire heat. Okay, good. So, now that universal equation for us MB mass balance for A, if I have a reaction A going to R, just I am imagining, okay, for easy writing. So, MB for A is what is entering this element Fa, oh sorry, I have to write the universal equation first, no, yeah, this is input equal to output plus short form reaction plus accumulation. Okay. All reaction engineers are steady state people, all process control engineers are unsteady state people, because they do not know what is steady state. Okay. So, that is why we happily assume that is not there, right. So, now we have only three terms: input, output, reaction. Of course, sometimes this also we have to use, and particularly when you are starting the reactor first, you should know under what at what time the steady state comes. So, for that to read definitely you have to again solve, but again that you will get depending on the equation, whether you get unsteady partial differential equation or the other ODE, ordinary differential equation, but that will come later when we are talking about residence time distribution. But this is the one of the simplest equations what you are going to get. So, this moles MB for A means we are also talking about moles per time, maybe second. This is better to write in the beginning, right. So, now Fa according to our notation, okay, I think maybe some other people are there. So, Fa is moles per time, moles per second for example, right, and V is meter cubed per second. So, this is called volumetric flow rate, this is called molar flow rate, and Ca naught is moles per meter cube. They are not universal. Please don't scold me when I give a problem in kilomoles, okay? Because I think either kilomoles or moles or lb moles also I can give, pound moles also we can give, okay, or meter cubed or feet cubed or centimeter cubed, okay, or millimeter cubed or whatever, right. So, that is this is only per unit volume, and Xa naught is conversion where there are no units. Similarly, this side also you have same thing, but we are now balancing moles per second. So, I have Fa equal to Fa plus dFa is the change here, that is the change, either positive or negative, okay, that will come automatically. Plus you have the reaction, where is the reaction taking place? That reaction is taking place within this volume. And what are the units of reaction rate? Because homogeneous we are talking right now, okay. So, moles per unit volume per time. So, that is why I will write here our rate is minus Ra, because always we write A as the key component. This is minus Ra, and I will also write here moles per meter cubed per second into volume is only dV. dV is meter cubed, okay. dV is meter cubed. So, meter cubed gets cancelled. So, I will have the entire only moles per second. So, my balance is right, okay, good. So, now this Fa both are same. So, I can bring here minus dFa equal to minus Ra into dV. If I call this one as equation, this is equation 1, this is equation 2, this is equation 3, right. So, in fact, I can simply write this equation as dFa by dV equal to minus Ra. By writing this equation is not useful to me, because I would like to put this equation in terms of easily measurable values. Fa is not that easily measurable, but I think I want to measure only in terms of conversions, concentrations or conversions, okay, good. So, now before going to that, okay, let me do that, and then afterwards we will simplify this. So, now for flow system, for batch reactor, how do you define conversion? For batch, how did you define? I think we also told, no? Na naught minus Na. Na naught is initial moles, minus Na is moles at any time. So, Na naught minus Na will give you, are you following? Na naught minus Na giving you moles converted, divided by initial moles, okay. But for flow system, we write the same thing as Fa naught, that is moles per time. They are simply moles you are taking, here per unit time you are taking. So, Fa by Fa naught. So, this is the definition of Xa. Now, from this can you calculate what is dFa? dFa differentiation, how much, what do you get?
Minus Fa naught into dxa into dxa
minus Fa naught dxa. You brought this one here into minus you put there, I think I will don't put minus here, minus dFa, okay. So, now this equation 6, these are very simple, but still I am explaining. So, now substitute that in equation 3, what do you get? Substituting in equation 3, substituting actually equation 6 in equation 3, what you minus the dFa I put here, Fa naught dxa equal to minus Ra dV. So, this is the basic equation which we use many times, particularly for non-isothermal systems in differential form. This is the design equation in differential form, okay. So, now we can integrate this. So, when you are integrating this, what we will change this one is dV by Fa naught equal to dxa by minus Ra. So, integrate. So, what are the limits? 0 to V and 0 to xa, right. So, I know 0 to V is simply V by Fa naught, 0 to xa dxa by minus Ra. So, this is the design expression for, this is 8, that is design expression for PFR, okay, the simplest design expression. Okay. Just for comparison, we have written for batch reactor, what is that? T by Ca not equal to same dxa by minus Ra, okay, just for comparison, right. Good. So, that is the one. So, now why this equation has become so simple? This is very simple. If I do not assume I have plug flow, because that I have to tell you, because assumption is one, but you have to also, you should have questioned me, sir, what will happen if you do not assume plug flow? What would have happened? If there is no plug flow, what is there in the system?
Concentration will change.
Huh? Louder.
Sir, no input and no output.
No, we have input and output. It is a flow system, but I am not assuming that I have plug flow. If I do not assume I have plug flow, then what is the non-ideality that comes? First non-ideality that comes, axial mixing. The velocity fluctuations, we are not allowing those fluctuations now here. So, the moment we have the velocity fluctuations, how do they look like? They look like this. Okay. Now, okay, to bring the point here, I can also write that Fa in terms of Ca. Can you write that? Molar flow rate in terms of concentration and volumetric flow rate. Yeah. So, that means I can also write here this Fa as V into volumetric flow rate into Ca naught, Ca. So, where do I write? Okay, I think here itself I will write. You can check the, I think I am worried about Arya and this Chaya, you are chemistry or chemical engineering. Yeah, you are able to follow? Okay. Yeah. So, this concentration you can you see, because I think we should help them. So, I am just telling even these things. So, this Ca, what are the units? Arya? Huh? Ca. Concentration. Concentration is always expressed per unit volume. So, moles per meter cube. And this one V? Meter cube per second. You write and tell me what are the units of Fa? Moles per second. So, that means even this I can replace by C and V. But we wrote directly that because that is the mass balance that gives me. I do not have to use two variables. But my biggest problem now is, because by assuming plug flow, right, what is the concentration across this? Uniform Ca. If I do not assume that, I do not have uniform Ca, then what is that I am writing here, this Fa? This Fa is indirectly Ca and V, and when Ca is not uniform, how can I write that? What concentration I take? Because concentration may be different here, different here, different here, different here, at that cross section may be different, because it is not uniform across the cross section. So, then what concentration I can use? What average? How do I know the average? How do you get the profile? So, finally you can do all that, but that is eating like this. Yeah, okay. But as an engineer, the simplest assumption, really we have to appreciate that Professor Denby. Denby is the person who has supposed to assumed these things. Even mixed flow also, he is the person who has done that. Actually, during Second World War, he was working in a explosive factory. Okay, and he was the person who told that, my God, if you use plug flow reactors, we will not be here in the company, because I think temperature control is not that very good in plug flow. Okay, so that is why CSTRs we have to use, and he started using 2 CSTRs and 3 CSTRs to produce all explosives. Okay, and later he has become great philosopher. Now he is still there, I think, but he stopped thinking about research. But I told you that chemical equilibrium, principles of chemical equilibrium, that book it contains wonderful information about entropy and all that. The moment you talk about entropy, immediately you can see God, because you don't understand entropy, you don't understand God. So that's why both are equivalent. Okay, so that's why now he is trying to find out where is God through entropy. Okay, he has become, I think he stopped it in basic research. But his papers, I tell you, if I have 1 or 2 papers, I will send it to you. But only thing is, I don't want to create e-pollution. Okay, so I don't know how many of you read my Feed the World. Okay, you see, that is what is e-pollution. If everyone reads it, very happy. Otherwise, why unnecessarily sending, and otherwise only those people can take from me. Okay, unnecessarily your computer also is overburdened. After one day, I think it may crash, because too many papers and all that. His papers, if you read throughout the papers, I think beautiful logic only, not mathematics. That is why you have to read that book, Chemical Reactor Theory, introduction. Even optimization, which has maximum number of mathematics in chemical engineering, optimization of chemical reactors, various methods. Even there, through logic, he has found out some conditions for optimality. Later, many people used many different mathematical techniques, and finally they said that what he has used intuitively was correct. Some conditions, and the non-isothermal time, I will tell you those things. So that is why the beauty of assuming plug flow is that the moment I don't assume that, okay, I will also give you an example. Okay, using this particular, the first thing what I want to tell you is, you don't know how to write material balance if you don't assume first of all plug flow, right? But you can also calculate, quantify things. Only one parameter if you take, called axial mixing. If you take axial mixing is there, and then try to derive the equation and get the equation for conversion. For first order, what is the equation for conversion here? First order constant density system. So that means I have minus RA equal to KCA. So substitute that in this equation, V by Fa naught equal to 0 to XA dXA by KCA, right? KCA. Can I integrate this directly? You have to write that in terms of XA. So that is why I have to write, okay, constants I will take out, K into CA naught dXA. It is a constant density system. That is why we said CA equal to CA naught into 1 minus XA. Okay, yeah, CA naught into 1 minus XA. So now this is equal to what? Minus log 1 minus XA. So if I calculate XA, tell me, 1 minus e power, again minus comes here, no? K CA naught V by Fa naught. Yeah, actually I don't have to use tau. Really, I think the natural design expression is, of course, time if you want to write you can, but the natural design quantity is V, volume. You directly get from these equations the volume itself. Later you want to convert means, okay. So what is tau here then? Yeah, in fact Fa naught by Ca naught is V. Fa naught by Ca naught equal to V. So V by V is tau. Then it becomes K tau. Right? Yeah. I mean, it is easy to remember K tau instead of remembering another 2 variables, because we should also should not strain our mind, no. Okay, why unnecessarily remembering unnecessary things. Okay. So that is why If I divide the Ca naught, then Fa naught by Ca naught will give me V, volume by volumetric flow rate will give me tau. So, then it becomes K into tau. So, this will be e power minus K tau, where tau is defined as volume by volumetric flow rate. Okay, are you able to see here? Yeah. So, that is nothing but in terms of this will be V Ca naught by, correct, Fa naught, yeah, V Ca naught by Fa naught. Okay, good. Now, if you do not assume this, yeah, you will get a very simple equation. If you do not assume plug flow and assume the first simplest non-ideality is axial mixing. We are not taking even radial mixing. You see, axial mixing is the one where you are getting, but radial mixing also can be non-uniform. Radial mixing. Okay. So, now we are taking only axial mixing is one variable first, right. If I take only that, that means I have plug flow, I do not have plug flow, but I have axial mixing coming as one of the non-idealities, because it is not ideal. That we are calling plug flow as ideal because we are assuming that this is the ideality what it should be there. Why? To simplify mathematics, that is very simple. Now, you see with this one, if I have axial mixing model, this is plug flow model what we have used, this one axial mixing model, and again first order, same first order constant density system, that is why I simply write KCA constant density system, A going to R. If I use that, then the equation which I get, okay, the equation which I get is this. Okay, I think for comparison, I think I will write this one, 1 minus XA equal to, first of all I have to draw this line, 4A exponential of UL by D whole thing divided by 1 plus A whole square exponential A by 2 UL by D minus 1 minus A square, again exponential by e to the power minus A by 2 UL by D. Very simple expression, no? Yeah, when compared to this, if I write this as 1 minus XA, this will be simply e power minus k tau. Okay. So, now this e power minus k tau, 1 minus e power minus k tau. Yeah. So, now it is not over, because what is A? You do not know it. Okay. Now, I have another equation for A. A equal to square root of 1 plus k tau d by UL, that is the equation, and we lost somewhere the numbers. This is 9, 10, 11, 12, 13. So, that is the equation what we have to use if you just consider only one parameter, that is you do not have that means the axial dispersion is always imagined as we have essentially the plug flow, that is not ideal one, but you have some fluctuations over that velocity profile. Okay, that will change. And how do I write this? Because now what is happening is, in earlier when I assume this, I think I have to discuss earlier when I assume that I have only plug flow. Okay, what mode is the flow inside the reactor? Because flow can happen by diffusion and convection. Diffusion is by concentration difference and convection by convection. Only velocity. Only velocity. Okay, yeah. So that means we have now two terms. One is convective velocity. Okay, so we will get convective flux plus diffusion flux. That is the total flux. Right. I will give you a simple example. So now I have the diffusion as well as convection both. Okay, this is convection plus this is diffusion. Convection is written as U into Ca flux. Yeah, this is minus D. Here I can take Z. Okay, if I take that one as Z or X whatever. Okay, so this is diffusion flux. So now at this point, now I have to write this is the flux flow. You see here I wrote actually moles per time. If I take per unit cross sectional area, because here cross sectional area is not changing, so that is why we are not taking per unit cross sectional area, because it is same diameter, right. But if I take that, that is a flux. What is entering here? Flux leaving there, and then what is the reaction inside, right. So of course correspondingly I have to also use this dV, okay, to get again moles per time. So that is why this is nothing but the flux which I have to write here. So these are the two terms now I have to use for solving the equation, and the differential equation what you get, yeah, for taking by taking this reaction and diffusion together, where you get this kind of equation is this particular one, U dCA by dZ, this is the convective term, minus d square Ca by dx square, yeah, plus K into Ca if it is first order reaction equal to 0. Okay, yeah, what is that I am trying to tell now? Yeah, you have to tell now. Yeah.
Actual dispersion.
See the earlier one which are actual dispersion model only, but why I am telling you actual dispersion model at this point of time now? To appreciate the beauty in assumption of plug flow. So what is the differential equation we got for plug flow? Pure plug flow. Yeah, you see that is dV, na? What is that? No, dFA by dV minus equal to minus RA. So this is the differential equation for ideal plug flow. I can write this in terms of conversions and all that concentrations also. Right, this FA is nothing but V into Ca. If I take V as constant, so this also can be written V dCA by dV equal to minus RA. Right. Now if I divide by cross sectional area of this and this, divide by cross sectional area of this and this, very simple I say, this will be velocity, and what about this one? Volume, this volume element I am now dividing by cross sectional area. Yes. So now this is dCA by dZ equal to minus RA. This is what I want to prove, how simple this equation is. Whereas this equation, this term. So to avoid this, first we are assuming that we have ideal plug flow. So all this last 10 minutes discussion is just to appreciate the assumption of plug flow, right. So for that, to give an example, because example will give you very clear picture what are the complications if you don't assume plug flow. The complication is this. Okay, this is the equation what you get for calculating conversion given volume. This is called dispersion number. D by UL is called dispersion number. D by UL equal to dispersion, no place also, okay. D by UL equal to dispersion number, okay. And inverse of this, yeah, if and I people use this, Peclet number, they call Peclet number, UL by D, right? Yeah, that will tell me what will be the dispersion. Like for example, when D by L equal to 0, what is the system?
Plug flow.
Well, D by L equal to infinity,
Mixed flow.
mixed flow. When Peclet number equal to 0,
CSTR.
mixed flow. Okay, when Peclet number equal to 0, because diffusivity is infinity, so that is mixed flow. And when Peclet number equal to infinity, plug flow, because diffusivity is 0. So you can get all the extremes by these two numbers. As I told you, high fund of people use this Peclet number, low fund of people like me use dispersion number, because I don't want to again use another subroutine inside my mind. Dispersion number is straightforward, D by UL, D is 0, plug flow, D equal to infinity, mixed flow, right? So that's what I am trying to explain to you. The beauty in assuming plug flow is simplification of the mathematical simplification of the problem, but you have to now question how far that is correct. Is it really correct? That is correct provided you take small tubes, okay, diameters maybe 1 inch, okay, around 1.5 2 inches, and maintain very high velocities. The dispersion, there will be dispersion, you can never neglect dispersion, dispersion will be there. So dispersion is we have very high, my mind has gone to time, so that's why. Okay, so very well valid in packed beds. In packed beds, what is the Reynolds number for turbulence? No idea. Okay, tell me when is laminar?
Less than 1.
In
Less than 1.
Less than 1 is Stokes law. Only single particle. In packed bed, how many particles you will have?
Less than 2000.
Huh?
Less than 2000.
Yeah, why 2000?
By
It is 10. 10 and less in a packed bed you will have laminar, and 500 above you have turbulence. In between you have transition. Okay, but here Reynolds number is defined how? Huh?
Diameter particle.
How normally Reynolds number is defined?
dV rho by
d rho by m. Here the d is diameter of the particle. There the d is
Diameter
of the pipe. So that's how it is defined. Okay. So the another example, I think today class itself I have to give that is I told you diffusion convection. I will give you an example, I think, so that you will not forget. Okay, 2 examples I will give. Imagine that I have come with a lot of scent, spray. Okay, scent means you may not understand. Okay, that is the old word scent. Okay, yeah, spray or deodorant, perfume. Very good, perfume. And also, by the way, perfumes are made by who? Chemical engineers. Yeah, all wonderful reactions, wonderful, that is low volume, high value product. Low volume, it will be 1 mm or 1 ml and 10,000 rupees. Stay there, can you smell me? If you have to imagine, I don't have right now spray. Okay, if I have all that perfume and then stay there, can you smell?
Depends on the humidity.
Why no?
At T equals 0.
Huh? It will take time. What is that time?
Depends on the humidity.
Diffusion. Till then, I did not ask you instantaneously you are able to smell. I did not tell that, no. Instantaneously smelling also is there. Okay. The other example what I want to give you is the conveyor belt again. Many people are standing on the conveyor belt, that is the convection velocity equivalent to, but some people, very enthusiastic people start working on that. So that is by diffusion equivalent, right? And what is the concentration difference? I mean, what is the gradient for them? Because here concentration gradient, but for the people who are walking, what must be the gradient? Maybe hurry, they have to catch the flight quickly, or they have to move, go quickly. So that's why those people are walking on the conveyor belt. Other people are cool, okay, let it take me whatever time that is possible, so they stand. That is by convection, normal flow. Above that again you have diffusion. So, now if you see axe advertisement, you should not forget convection and diffusion, and also now if you see conveyor belts, again convection and diffusion. But in ideal plug flow, that diffusion is not allowed. In ideal plug flow, diffusion is not allowed. Okay?